24,000 containers, 400 meters of steel, 13 people. That is the entire crew keeping $1 billion of goods alive on open water. $1 billion worth of goods across an ocean while the rest of the world sleeps. Right now, somewhere between Asia and a port you have never visited, a ship the length of 4 football fields is cutting through open water. It carries the phone in your pocket, the shoes on your feet, the components inside whatever device you are watching this on, and the people responsible for all of it. 13. Fewer than a restaurant staff on a Saturday night. The real question is not how something that large stays afloat. The real question is who decided this was the shape the world should take, and why nobody told you. The last time a package arrived at your door, you did not think twice. But somewhere inside that transaction was a ship, probably a massive one, and the entire chain of your daily life ran quietly through its hull. Your coffee maker, your medication, 90% of everything you own at some point crossed an ocean inside a steel box stacked on a vessel you have never seen and never thought about. Nobody made that invisibility by accident. It is a design choice, and it has a cost that only becomes visible when the system breaks. When the Ever Given wedged itself sideways in the Suez Canal in March 2021, it did not just block a waterway. Factories in Germany went idle. Car dealerships in the United States ran dry. Grocery shelves in countries that had nothing to do with Egypt quietly emptied. One ship, 6 days, billions of dollars, and 3 continents feeling the pressure. And that happened by accident. So ask yourself, what happens when something goes wrong by design? Here is what the next few minutes are going to establish. First, the physics. Why something this massive floats, and why the answer is stranger than most people expect. Second, the stacking logic. How tens of thousands of steel boxes stay upright in open ocean without turning the whole structure into a slow-motion collapse. Third, a quiet meeting in the 1970s between engineers whose names appear in no textbook, whose choices now dictate what sits on your shelf. And here is the thread that runs through all 3. The reason this ship floats is inseparable from the reason a very small number of people control it. Those 2 answers are the same answer. Start with the physics, because the physics is where the conspiracy hides in plain sight. A steel spoon thrown into a sink vanishes beneath the surface in under a second. Take that same mass of steel, reshape it into a shallow bowl, and it rests on top of the water. Nothing about the material changed. Nothing about gravity changed. What changed was the volume of water being pushed aside. Buoyancy does not care about weight in isolation. It cares about displacement, the weight of the water that a submerged shape forces out of its own space. If the displaced water weighs more than the object floats. Archimedes worked this out in a bathtub roughly 2,200 years ago, and every container ship afloat today is still running on that same arithmetic. The hull of an ultra-large container vessel is engineered to push aside an almost incomprehensible volume of seawater. The displacement of the largest class of ships currently operating reaches around 240,000 tons. That number means the hull is continuously forcing a mass of water equivalent to roughly 240,000 small cars out of its path. The hull wins that contest, not because it is light, but because it is shaped to occupy an enormous volume while keeping most of that volume hollow. The steel is real. The cargo is real. But most of what the ocean is actually supporting is structured empty space. That same rule that makes the scale possible also caps it. There is a hard ceiling. Once the displaced volume cannot be increased further without violating either the hull's structural integrity or the depth of the ports The ship needs to enter. Growth stops. The architects who fixed those limits in the 1970s understood the arithmetic would never change. What they may not have fully understood is what concentrating the world's cargo into the fewest possible holes would eventually mean for everyone else. The ship floats. Fine. But now consider what sits above the waterline. 24,000 containers stacked 9 stories high on an open deck, fully exposed to the sea. The moment a crosswind hits that wall of steel boxes, the leverage is enormous. Picture a sail the height of a 9-story building and the length of 4 football fields. The ocean does not ask permission before it pushes. So how does the whole structure not simply topple? The answer lives in the numbers below the surface. The largest holes draw 16 meters of draft. That is the depth of a 5-story building hanging beneath the waves before a single container is loaded. The submerged hull volume equals roughly 70 Olympic swimming pools, compressed into a single steel cavity. That mass, that depth, that volume together force the center of gravity so low that the ship's own weight becomes the counter-argument to every gust of wind. Naval architects use a concept called the metacenter, an invisible stability point, and they treat it with something close to reverence. The metacenter is an invisible point above the ship's center of gravity. When it stays above the center of gravity, any tilt the ship experiences generates a restoring force that pushes the hull back upright. Once the metacenter drops below the center of gravity, that tilt becomes self-reinforcing. The ship rolls farther, water floods the decks, and recovery is no longer possible. The formula is 2 letters. G below M means the vessel survives. G above M means catastrophe. There is no middle position. The margin is absolute and unforgiving. Maintaining that margin across every possible loading configuration is why container ships carry ballast tanks, whose only function is to drag the center of gravity downward. Before departure, the loading computer fills or empties those tanks with surgical precision, shifting thousands of tons of seawater until the invisible geometry holds. Those tanks are not optional equipment. They are the final correction for decisions made decades ago about hull shape, stack height, and cargo density. One miscalculation in that chain, and the entire vessel becomes a floating lever, waiting for the next wave to complete the job. The industry would rather leave one question unanswered. Rather, leave unanswered. Every container on that ship carries a declared weight, a declared contents list, and a GPS-assigned slot number. Every single one. But who actually verifies any of that before it goes aboard? The loading computer runs stability simulations for each placement, calculating how that one box shifts the relationship between the center of gravity and the metacenter. Heavy containers are assigned to the lowest rows along the center line. Light ones go high and outboard, spread wide to preserve the righting moment. The entire vessel is a 3-dimensional weight puzzle, and every placement changes the solution. 24,000 containers, each one a variable. The software treats the ship as a living equation, and the load plan that emerges looks less like a cargo manifest and more like an architectural blueprint. Longshoremen follow it, crane by crane, slot by slot, in a sequence that cannot simply be reversed if something goes wrong. Mid-port. The system assumes the declared weights are accurate. It assumes the contents match the paperwork. It has to. There is no practical way to open every box and verify what is inside. So the most sophisticated loading algorithm in maritime history sits on a foundation of declarations made by strangers in warehouses on the other side of the planet. That gap between the model and reality is not a minor administrative detail. It is where the structural vulnerability of the entire system becomes fully visible. Now add one more physical fact that almost nobody outside the industry ever thinks about. Right now, somewhere in the middle of the Pacific, this ship is bending. Not breaking. Bending. The hull flexes with every wave cycle, and that is not a flaw in the design. That is the design. Here is the specific problem. A wave that is longer than the ship is actually more dangerous than a wall of water. When the crest passes under the midship section, the bow and stern are both resting on water, while the center of the hull hangs unsupported in open air. That condition is called hogging. The hull bends upward at the center. Then the trough passes through, and the center drops, while both ends are lifted. That is sagging. The hull cycles between these two states continuously, absorbing a bending moment that engineers describe as comparable to suspending the Eiffel Tower by its center point, not once, but repeatedly, every few seconds, for an entire voyage across the Pacific. A 400-meter hull made from conventional steel would simply fail under that load. What keeps it together is the hull girder, a continuous structural beam running the ship's full length. A continuous structural beam running the full length of the ship, formed by double hull plating, the deck, the keel, and thousands of internal frames acting as a single unit. The outer and inner hulls are separated by a void space roughly 2 meters wide. That gap is not wasted room. It is the margin between the ship surviving a collision and flooding in under 6 minutes. The naval architects who calculated these tolerances worked before computer modeling existed. They used tables, slide rules, and beam bending theory that dates to the 19th century. And those same fundamental limits are still embedded in every container ship afloat today. The calculations are old, the ships are newer, the assumptions connecting them have never been seriously revisited. 6,000 container ships are cutting through open water right now. The system never stops. And the largest of those ships, the ones moving the volume that keeps factories running and shelves stocked, are controlled by 5 companies. Not 50, not 500. 5. That number is not a coincidence, and it is not the result of a free market finding its natural equilibrium. It is the result of quiet decisions made by people most of us will never hear of. Decisions made before the internet existed. The origin traces back to 1972 in a conference room that has been almost entirely erased from public memory. The United Nations Committee on Trade and Development, UNCTAD, gathered the major shipping nations and did something that rewired the entire global economy. They standardized the box. 20 feet, 40 feet. Those 2 dimensions, locked in and agreed upon, became the invisible skeleton of the modern world. Every port, every crane, every ship designed after that moment was built around those numbers. And once the box was fixed, the only variable left was how many boxes could be stacked on a single hull. That is when a specific assumption entered the system. An assumption that nobody debated openly and nobody voted on. Naval architects working through the mid-1970s built their cost models around one relationship. Slot cost falls as the ship grows. The more containers per vessel, the cheaper each one becomes to move. On paper, the logic is clean. In practice, it became something closer to doctrine. Bigger ships did reduce cost per slot. The model kept confirming itself. So the architects who designed the next generation of vessels simply scaled the assumption upward, and then again, and then again. But the model had a question buried inside it that nobody asked out loud. Efficient for whom, exactly, and measured over what time horizon? The shipowner sees a lower cost per slot. The port that lacks the dredging depth to receive the vessel sees paralysis. The manufacturer whose single-source supplier misses a sailing sees a production line stop. The model counted one kind of efficiency and quietly ignored 3 others. And because the people running that model were not elected, not publicly accountable, and not required to explain their assumptions to anyone outside their own firms, the question was never forced into the open. The result is a system with almost no redundancy and almost no margin for error, a system that revealed exactly what it was the moment one hull stopped moving. March 2021. The Ever Given swings sideways in the Suez and simply stops. 369 vessels line up behind it, each carrying goods already priced and promised to buyers on the other side. Trade worth $9.6 billion a day stands still. No backup route exists at that scale. Salvage crews need 14 tugboats and a full moon tide just to drag the hull free. The blockage lasts less than a week. The delay ripples through factories, warehouses, and store shelves for months. The same naval models that had rewarded ever larger hulls for 50 years offered no plan for what happened when one of those hulls could no longer move. The efficiency calculation had treated the canal as an infinite pipe. The canal treated the ship as an immovable object. Both assumptions had been allowed to stand unchallenged until the moment they collided. One ship, one canal, 6 days, and the global economy visibly flinched. What does that tell us about the redundancy built into a system that carries 90% of everything? Here is the answer to both questions at once, the physics and the politics, because they are not separate subjects. The ship floats because it displaces roughly 240,000 tons of water, and ballast tanks in the double hull are filled or emptied with precision to keep the center of gravity exactly where the calculations demand. The physics is not mysterious. The unsettling part is not the how. It is the why, and both point to the same object. The very displacement math that makes 24,000 containers possible is also the math that produces a hull too wide for the original Panama Canal locks, too deep for most secondary ports, and too large to reroute without cascading costs that no single insurer will fully cover. The engineering solution and the systemic vulnerability share one body, and that body was not chosen by market forces. It was not chosen by democratic consensus. It was chosen by a small cluster of naval architecture firms working from standardization models drafted in the 1970s, models that treated concentration as a synonym for efficiency and never asked what efficiency was actually for, or who bore the cost when it failed. 5 carrier alliances now operate roughly 80% of global container capacity, using vessels designed around those same assumptions. Ports rebuilt themselves to receive these ships. Supply chains rebuilt themselves around those ports. The world did not drift into dependency on a handful of ultra-large hulls by accident or by market evolution. It was calculated there, slowly, by people whose names appear on no ballot, whose decisions appear in no headline, until one of those hulls stops moving, and suddenly, everything else does too. The scale keeps growing. The rules underneath it have not changed. Buoyancy is still the law Archimedes described 2,200 years ago. The box is still the dimension fixed 50 years ago. The ownership structure hardened 50 years ago. The gap between how large these vessels have become and how thoroughly their assumptions have been pressure tested is not a gap the industry likes to discuss. The risk does not live in the ocean. It lives in the unchecked growth of a system whose original architects never imagined it reaching this size. The next time a package is late, that delay traces back to 5 boardrooms that locked a set of dimensions into place before most of their current customers were born. The ship floats because the math works. The harder question is whether anyone ever actually designed that world, or just inherited it to hold.